When dealing with processors or microcontrollers, we can create a routine for them to follow using predefined programming instructions tailored to that specific processor. So, in the world of processors, the programming language is like a tool that helps you convey your ideas to the processor. But what happens when we shift our focus to FPGAs? How do we go about explaining the digital circuit we've envisioned or designed on paper for FPGAs? In this video, we'll delve into the process of describing a digital circuit for an FPGA, or more specifically, for the implementation software. As a quick refresher from our previous videos, we discussed the fundamental concept of FPGAs and how circuits are implemented within them. We mentioned that within an FPGA, circuits are built using the available hardware resources. But here's the question. How do we initially describe a digital circuit for an FPGA? There are generally two primary methods for describing circuits for FPGA. The first method involves using circuit schematics. In this schematic-based approach, you use a software tool, also known as implementation software, along with basic digital components defined in that tool, such as gates, flip-flops, multiplexers, encoders, decoders, and so on, to describe the circuit intended for the FPGA. By utilizing these building blocks, you can sketch out various circuits for the FPGA and describe their functionalities. Although this method may appear straightforward, the reality is that it's not particularly practical. Imagine you're tasked with designing a circuit containing thousands of gates and digital components. Firstly, fitting this extensive design onto your small computer screen can be quite difficult. Now, picture this. You have successfully drawn the circuit, but then you discover an error or need to make a modification. It becomes a complex and nearly impossible task. For this very reason, when it comes to describing large circuits within FPGAs, there exists another method that involves the use of hardware description languages, or HDL. An HDL is a specialized language designed with constructs and expressions that enable us to describe how a digital circuit behaves. Unlike traditional programming languages that deal with commands or instructions, HDL isn't composed of commands because commands are primarily associated with CPUs. As you are aware, FPGAs don't initially come with CPUs or any other pre-built hardware components that represent specific features. So an HDL isn't a language made up of commands. Instead, it contains constructs and expressions that, while they might resemble programming commands at a glance, are in practice used to describe digital hardware. Let me clarify the concept of hardware languages using another example. The code you're seeing in this figure is a construct called an if-then-else conditional in the programming world, and it's found in nearly all programming languages. If you imagine this as a part of code written in the C language, for example, which is intended to run on a processor, then the if-then-else instruction has already been defined for the CPU. When the CPU encounters this instruction, it checks the value of C. Depending on whether C is 0 or not, it will copy either the value of A or B to a variable called F. Now, let's switch gears and consider these statements as descriptions of digital hardware. What digital hardware does this code describe? Yes, you got it right. These statements are actually describing a 2-to-1 multiplexer. In a 2-to-1 multiplexer, depending on whether the select line C is 0 or not, either input A or input B connects to output F. As you can see, this code precisely represents and describes this digital concept. So as you've observed, in this hardware-focused code, there isn't an instruction meant for execution by a CPU. Instead, we have a description of a digital hardware circuit. Now, there are various hardware description languages out there, but the two most well-known and widely used ones are VHDL and verilog. While these two languages may have differences in their appearance and syntax, both of them allow you to define any type of digital circuit. Let's delve a bit deeper into VHDL, which stands for VHSIC Hardware Description Language. The V in VHDL stands for Very High Speed Integrated Circuit. So VHDL stands for Very High Speed Integrated Circuit Hardware Description Language. Interestingly, VHDL was initially developed by the US Department of Defense. In the beginning, its main purpose was not to implement digital systems, but rather to document circuits that had been previously created. Another goal behind creating this language was to enable digital circuit modeling. However, as time passed, VHDL found its use in implementing digital systems as well. Ultimately, the IEEE organization standardized this language in 1987 as part of the IEEE 1076 standard, and the VHDL we use today is the standard language recognized within the IEEE organization. Well, as I mentioned earlier, VHDL isn't a programming language. Rather, it's a language used for describing digital circuit. Now, let's get to know the structure of the VHDL language. In a nutshell, every VHDL code can be divided into two main parts. I'll walk you through these two parts using this figure. In this figure, imagine we have an IC or a digital circuit. Typically, we can break down this digital circuit into two key sections. One part includes the pins or input-output ports, while the other parts forms the internal circuit. In VHDL terms, the pins or input-output ports go by the name entity, and the internal circuit is referred to as architecture. So in a VHDL code, you'll generally find two main sections. The first part is known as the entity, and the second part is labeled as architecture. In the entity section, our primary task is to define the ports. This involves giving names to the ports and specifying whether they are input, outputs, or bidirectional. We also determine the type of these ports. However, the meaty part of a VHDL code, which is the architecture section, is where we start describing the digital circuit itself. To become even more familiar with VHDL, let's go over an example together. In this figure, you can see a full adder circuit along with logic expressions associated with its output. As you might recall from logic circuits, a full adder takes three inputs, A, B, and carry in or C in, and it produces two outputs, sum and carry out or C out. The logic expression for sum is the result of an XOR operation on all three inputs, while the logic expression for the carry outs is A and B or A and C in or B and C in. To describe this function in VHDL, we need to first define the inputs and outputs using the entity and then describe the circuit in the architecture section. This circuit involves three inputs, A, B, and C in, and two outputs, sum and C out. We can define these using the entity part in VHDL. Now, in this concise code, you'll find the entity section that starts with the keyword entity, followed by the name of the entity full adder, and then the keyword is. Within this section, we introduce the ports. For example, to define the first port A, we first specify its name. Then, after the colon, we determine whether it's an input or an output. In this case, it's an input, so we use the keyword in. Finally, we specify the port type. Here, we've used the type std_logic, which we'll discuss in more detail in future videos. Once we've defined the ports, we move on to describing the internal circuit, and we do that in the architecture section. The architecture section begins with the keyword architecture, followed by the name of the architecture, then of, the name of the entity, and is. After the keyword begin, you're ready to describe the internal circuit within this area. Thankfully, VHDL already includes basic functions like AND, OR, NOT, XOR, XNOR, NAND, and NOR. With these, we can generate the sum and cout outputs. For example, to compute the sum output, we've written A XOR B XOR Cin on this line and assigned it to the sum output. To assign the result of this logic expression to the sum output, we use the less than or equal to symbol in this language, which is often referred to as the assignment operator. So this was a straightforward yet complete circuit for implementing a full adder in the VHDL language. In upcoming videos, we'll delve deeper into VHDL's feature and tackle the implementation of more complex circuit. I hope you enjoyed this video and found value in it. If so, please give this video a like, and if you are not already part of the community, hit the subscribe button and the bell icon to be notified each time I share a new video. Let me know in the comment if you have any questions about the circuit implementation on FPGA. I'd love to hear from you. Thanks so much for joining me. I'm Ahmed Sagafi, and I see you next time.